I'm now a postdoc from the system group ETH Zurich. Today it's my pleasure to have a talk here. My talk is about the database techniques for machine learning systems. The goal of my talk is to teach a new old tricks. So actually, what I want to say is to teach machine learning system all the database tricks. Actually, I want to apply the database bit serial memory layout to the machine learning systems. In particular, I will compare the database predicate evaluation with the machine learning's low position and the bit serial memory layout. Actually, as a result, it turned out that the bit serial memory layout works surprisingly well for machine learning systems low position. Even better for the database predicate evaluation. Here's the outline. First, I will talk about the low position. So why we need a low position. So what we expect from a low position. Then I will talk about the bit size memory layout. What's the bit size memory layout, and how bit size memory layout perform. Lastly, I will talk about compare the machine learning with database and the bit serial memory layout. And I will explain why the bit serial memory layout is better for machine learning. First, I will talk about the low position. So suppose we have a machine learning model. The output machine learning model will be from 0 to 1. We assume that suppose the output is from 0.5 to 1, we can claim that the input image contains a cat. So now I will explain give the intuition why low position works for machine learning. So I assume that the machine learning model contains a simple multiplication here. So the multiplication can be done in full position, like in left side. It can also be done in low position, like the right side. So actually, the low position can still do really good job because its result is 0.78 is still larger than 0.5. It can tell that the input image contains a cat. So actually, it's just machine learning. So low position works, but probably you know that the low position probably doesn't work out in database. For example, suppose you have $1.3 million in your bank. Then the bank tell you that I want to do the low position. Then your account will have just $1 billion. You will get freaked out and then just change the bank. Right? Actually, probably for different machine learning model, you need different positions. For the first one, probably you need 3 bit. For the second one, probably you need 9 bit. But unfortunately, current hardware cannot support low position pretty well. For example, the current CPU can only support 8-bit, 16-bit. For the GPU, can also support 8-bit and 16-bit. For the TPU, only support like 8-bit. But your model probably you want 3-bit. What you can do, you can only just padding 3-bit to 8-bit for the further computation. So it means that you cannot fully take advantage of low position given the current commercial hardware. So here's the question is, can we work out one solution that supports any position? So our answer is yes, but we need some help from database community. In particular, we want like the bit serial memory layout. Now I'll talk about how bit serial memory layout works. So what's the bit serial memory layout? Suppose we have one column, and the column have like 4 values, and we want to perform predicate evaluation on this column. And now I will talk about how do we store this column in bit serial memory layout. Before I talk about bit serial memory layout, I will talk about how to store this column in normal memory layout. First, I will store the first value, followed by the second value, and the third value, and the fourth value. Then I will talk about how to store this column in bit serial memory layout. So here's the difference. We will store the first bit of all the value of this column together, followed by the second bit of all the value of this column. Then the third bit and fourth bit. So then we can do the practical evaluation on the bit serial memory layout. So with the bit serial memory layout, we can break down the evaluation into bits. We can first compare the most significant bit, the first bit. Suppose it's equal, then we need to compare the second bit, and if it's equal again, then we need to do the third bit. But if it's not equal, then it means that the comparison result is deterministic. So you can just early stop. Now I will use the example. Suppose we perform the practical evaluation on the first value. We first compare the first bit. Its first bit is equal to the first bit of the comparison constant. So we need to proceed to the next bit, the second bit. But we found that the second bit is different from the second bit of comparison constant. So we can stop here. Now we can just move to the second value. Because the result is determined, we don't need to evaluate the third bit and fourth bit of the first value. For the second value, we compare the first bit, is the same, we need to compare the second bit. It's the same, we have to go to the third bit. It's the same, we have to compare the fourth bit, so on and so forth. So we can see that we only need to evaluate the bits, not all the bits. But we found that practical evaluation leads to irregular memory access pattern and the bit serial memory layout. Now then I will talk about how bit serial memory layout works for machine learning low precision. So for the low precision, suppose we want 1 bit precision, so we only need to read the bits in blue with the first bit. Suppose we want 2 bit precision, we only need to read the bits in blue and orange. Then here we can find that the low precision leads to regular memory access pattern. Now I will talk about how to intuitively show the cost of practical evaluation on the bit serial memory layout. So actually, when we evaluate the predicates on the values, we do it in a value central view. Essentially, we will do like first on the first value, and the second value, and the third value, and the fourth value. But actually, we cannot. It's really difficult to have to find the performing characters in value central view because each value might need a different number of bits to evaluate it. So our solution here is like we can convert a value central view to memory region central view, like in this way. So in memory central region central view, so we can see that for the memory region for the first bit, each access leads to cache hit and also collective branch prediction. So it's quite good. But for the remaining memory region for the second and third and the fourth bit, each access will lead to a cache miss and also branch misprediction. So actually, based on our macro benchmark, we can see that the cost difference can be up to 2 orders of magnitude or 2-3 orders of magnitude. So it's quite different. Now I will show how the cost for the low position on the bit-serial memory out. So for the 2-bit position, actually each access will need to cache hit and also correctly branch prediction. This is the fundamental reason why I want to say that the bit-serial memory out is better for the machine learning's low position, not for predicates. So we can say that bit-serial memory out works better for machine learning low position. And if you want to know more about the bit-serial memory out works for machine learning low position, please attend my talk in Vivian tomorrow. It will be the research session 8, hardware and machine learning. Now I will tell you goal of this talk. I really want to say we can apply or should apply more database triggers to machine learning systems because the machine learning system is kind of new, needs more improvement, and also you guys are database experts and maybe have a lot of database tricks, and maybe you can find better application in machine learning systems. And I think it will be a fruitful research direction there. Yeah, that's all. Thank you. Any questions?
Any questions? Can you use a mic?
So I just have a quick question. So do you have any numbers on how much lower precision would you like to accuracy of the model? Like that before
Sorry, I can't hear you.
sorry.
Hello? Yeah, can you hear me, John? All right, so yeah, I just have a question about, do you have any numbers on comparing different precisions, like FP4 compared to FP8, FP16? Like how much the impact of lowering the precision will cause leads to the accuracy of the model?
Based on my current experience for the linear model, I think it should be 4 bits will be enough. Maybe for the most case, 4 bits to 6 bits will be enough.
Is it model dependent? Like, are we talking about neural network or is it same thing?
Just for linear model.
Just for neural network.
Yeah.
So do you have any numbers that you can show maybe? Some comparisons between lower precision versus higher precision in terms of the accuracy of the model?
I think for 6 bits, you can just have the same, roughly the same accuracy, test accuracy as the full precision. I mean, for the floating point, compared with the floating point.
So it won't impact the convergence speed of the model?
Say it again? Sorry.
So the lowering precision won't impact the convergence of the model, right? It won't delay the convergence of the model?
No.
Thank you.